Okay, so now we've seen two examples, factorial and sum digits. And for each example, we've seen two versions. One version which follows the mathematical definition, and another version which follows another idea called the principle of communicating vases. In both of these examples, the second version, the version that uses the principle of communicating vases, has a particular interesting property. The property is that the recursive call is the last operation done by the function. So the recursive call is the last operation done by the function. Okay, this particular property is called tail recursion. Now, what's so special about this property? Well, in order to understand what's special about this property, let's take a look at the factorial. And let's take a look at both versions and what the recursive call looks like. So the first version, the recursive call looks like this. N times fact 1 of n minus 1. So what's so special about this particular version? Well, look, the factorial, the recursive call here, it's not the last operation. In fact, once the factorial operation is done, the system has to come back and do this multiplication, okay? So the multiplication has to be done, has to come back and do it, this, for the multiplication. Okay? And that's kind of a problem because when the factorial is being done here, where is it stored? So the multiplication has to be stored somewhere. In fact, it's stored on a stack. Because why a stack? Because each recursive call has to come back and do multiplication. So I do for one recursive call, the multiplication is stored. I do the next one, another multiplication is stored, and so on. So I have to store one for each recursive call. So I need a stack. And the depth of the stack depends on how many nested recursive calls there are. So that's the first version. Let's look at the second version now. The second version, the recursive call looks like this. Fact 2, we have I minus 1, and then we have I times A, like this. Now, notice that the recursive call is in fact the last operation. We prepare the two arguments here, I minus 1 and I times A. We give them to this fact 2 call, and nothing has to be done when it comes back. Doesn't need to come back. So the stack size is constant in this case. No stack is necessary, in fact, for this, because when it goes forward, it never has to come back to do an operation. So stack size is constant. Okay, so that's very important. That means that this second version here behaves exactly like a while loop. A loop which can execute many iterations without using more memory. It's the same for this second version. It can execute many recursive calls without using more memory. Okay? So this is the rule. when you write a recursive function, the recursive call has to be the last operation. If you do that, then the stack size will be constant. So in other words, you have to use tail recursion in order to write loops in the functional paradigm.